welcome ATDC and welcome Lady Irwin College students and faculty. Uh, we have collaboration agreement with all three institutions which are part and parcel of this endeavor. And in place of the physical delivery of specialist lectures, we have, under the current circumstances, we have been arranging for webinars to take place. Today, our distinguished speaker is Dr.Debasish Banerjee, who is a fellow of the Textile Institute. And I have great pleasure in welcoming him to the webinar.
Thank you, sir.
Dr. Banerjee is an accomplished person currently working in East Africa, in Kenya, but he has a large number of achievements to his credit. I'm sure you will enjoy what he has to convey to you in the presentation. Hopefully, you might have read whatever resource materials he has provided in advance. So welcome students, faculty, and all other interested professionals who have joined. And I wish you a pleasant evening in this webinar. Over to you, Debasish.
Thank you, Dr. Shanbag, and to all the members of the faculty of the various institutes, as well as Mr. Shailesh and Dr. Mukesh, Mr. Chatterjee, and every one of them. Thanks for giving me the opportunity to present this webinar series, importantly for me. Am I audible to everyone around?
Yeah, you're
Yes. Am I audible, sir, to all of you?
Yes.
yes.
Yeah, I'm just muting myself. Sorry, just hold on. I'm just muting myself.
So shall I continue or shall we wait for someone?
No, please do. Please continue.
Okay. So thanks again for the opportunity provided to me to present this webinar, but more importantly for my career so far and my work is centered around transforming organizations. And the very purpose of this presentation is to provide you insights, provide insights to the textile industry to change track. Because I believe you would be concurring with me that the state of the textile industry as of now, or for the past 15 or 10 years probably, has been progressively declining. Although India as a country is at a vantage position for so far as the textile value chain is concerned, because of the expertise that is available in the country. But in spite of that and the opportunities around the globe, as one of the major textile producers, we have not been able to capitalize on the opportunities. And right across the industry, we see a situation where most of them are struggling for profitability and even volumes. So the essence of my initiative in this presentation is to give you insights probably from a detailed engineering perspective, wherein we look into the grading of cotton, the yarn engineering process in a realm of mechanical engineering, as well as, of course, the hardcore textile engineering, and a fair amount of mathematical modeling into the structuring of fabrics and establishing a prediction mode. At the end of the day, we should be in a position to predict problems and defects in the entire process chain. And that prediction, if we are spot on, we will be in a position, we will be in a vantage position to troubleshoot way before the problem has manifested in the fabric or in the garment stage. So that's the reason why I started the entire initiative. I mean, my presentation is centered around garments because that's the final cog in the wheel, so to speak, or rather the terminal point on the value chain. So it's very expensive if the garment is defective. In the yarn process, we really can cut down on the cost of defects, but at the stage of the garment and the fabric, of course, we don't have. It's a very expensive proposition. So that's more the reason why we need to understand the prediction mechanism and the mathematics involved in the prediction of defects and more importantly, in establishing productivity in the value chain on a consistent mode between batches and across batches. So the first slide, if you look at in my presentation, is algorithm for fabrics. Algorithm is, of course, everyone knows algorithm is a mathematical model to generate a so-called expert software or expert opinion. So, the software is primarily a human being, a human interface. For instance, you want to use my expertise day in and day out, 24 hours, 365 days without my intervention. So I would create an algorithm which will be replicating my expertise into the process. And you will be able to access that expertise anytime, 24 hours, 7 days. That's what the algorithm is all about. It's all about creating a mathematical logic which might replicate my thinking process. I'm just giving an illustration. It could be anyone else for that matter. But I'm just giving you an illustration that if you want to replicate my expertise into the process and establish a solution, maybe a software which will read my mind, which will read my process troubleshooting mechanism and create an algorithm. Algorithm is fundamentally logic, a mathematical logic for creating whatever you want to create. In our case, we are creating fabrics from a logic of yarns. So in my what we call talks this evening, I will be focusing essentially on cotton, exclusively on cotton, because the time is limited and the scope is also limited. We are not moving into polyesters or other man-made fibers. We're just focusing on cotton. So if you look at fabrics, sir, or I mean the entire audience, you need to appreciate that the fabric is a function of the fiber dynamics. What kind of fibers you have and how the fiber behaves right across the yarn process, as well as the mechanical processes of knitting and the weaving and the whatever. And of course, how the dye uptake is happening, the dye affinity is happening. When you do look into the processing parameters, the wet processing parameters, you will be essentially looking at the fiber characteristics. But the textile world, as of now, I'm sorry, I'm going to use very strong words. Please do not mind my words, but I'm essentially using very strong words because the textile industry has not yet understood the nuances of the fiber dynamics. We are still in the level of evaluating HVI and APHIS and probably looking at fibers as a discrete model. When I say fiber as a discrete model, we are looking at individual fibers, we're looking at the population, and we try to segment it at 50% span length, 2.5% span length, and so on. Or probably we'll look at the tensile properties, we'll look at the elongation and the elongation of break, or the work done to break, or the stress at break, breaking stress, and so on. But that is a discrete model. In a mathematical world, discrete models do not generate predictions. Predictions can only come when you replicate, when you normalize a discrete model into a continuous model. So what we are dealing so far is a binomial model where the fibers are looked at from a perspective of a family or a batch. It is never treated in a continuity. And that's probably the reason we look at the discrete values and try to figure out whether there will be some sort of continuity. We look at the upper bound, the lower limits and upper limits, and try and figure out what could be the best balance. And in that balancing act, we end up having barre, we end up having dyeing properties, variation in color, variation in color tone, and so on, apart from the host of mechanical issues. But in my presentation right now, I'm beginning with understanding that fibers are basically waves. They are waves, and they are a Fourier transform. Fourier transform is essentially a periodic wave with a certain amplitude and a certain wavelength. The wavelengths can be changed, wavelengths can be varied, and the amplitudes can also change and vary. But we can mathematically predict what should be the bandwidth of variation of the amplitude and the bandwidth of variation, even the wavelength. For example, if I trigger a wavelength change, how does the wave behave? How does what are the harmonics hidden within the wave systems? And that is what a Fourier transform essentially is from a mathematical perspective. and I want to put it into the fiber dynamics, wherein I'm looking at the length distribution. There are two factors that really matter. If you probably, I sent you a spreadsheet modeling wherein the fiber is looked at into only two methods. One is a length, another is a spatial angle. Spatial angle is naturally what is the inclination of the fiber. You know, the fibers, depending on the growth areas, for example, is a Peruvian or is a Brazilian cotton or wherever, North American cotton or the US cotton, or for that matter, the Indian cotton among the Indians, the J34, Shankar 6, whatever you say, BT. Each variety of cotton has got a natural genetic value for a space, the space it describes and the angle it describes, and that is what is known as spatial angle. When I say spatial angle, what is my natural inclination from a vertical axis, or from a linear axis for the matter, not a vertical, I would say, I'm sorry about that. It's a linear axis. So what is the inclination? What is the torsion? Natural torsion. Natural torsion means you're not subjecting the fibers to a stress on its own. It has a natural inclination to a Z direction maybe, or an S direction. And what is the natural angle it describes if there are no stresses? Now, how does it matter? It matters because if you're let's say you have two different growth areas. One growth area is at a torsion angle of 30 degrees. Another growth area is at a torsion angle, natural torsion angle of 45 degrees. Maybe we are assuming, for the sake of assumption, length and all other parameters which we normally evaluate are identical. But let's say Peruvian cotton is 45-degree angle. Another Indian cotton, maybe typically 25-degree angle. Now, if you compare the natural torsion angle of 20 to 25 degrees Celsius and compare it with 45 degrees Celsius, what is the big difference? The big difference is, in order to extend, in order to perform the work for a bunch of fibers, you have to do enormous work if the angle is higher. For example, 45-degree angle, natural angle, will require a large quantum of work to be performed in order to extend it to the point of rupture. So in the process, your elongation will be typically higher. And that is true. You might see that the North American cottons will have an elongation which is significantly higher than the Indian cottons, naturally. The reason is your spatial angle typically is higher by at least 15 to 20 degrees. And therefore, in order to bring down to, you have to first perform the work to align it linearly and then extend it to the point of rupture, to the point of fatigue, and then eventually rupture. So all this entire process requires a lot of elongation. I mean, the elongation at break obviously extends. So tensile properties of the fibers are more, to my understanding, is basically a function of the spatial angle it naturally describes. Everything else remaining the same. Of course, the processing parameters do make a big difference, but we are assuming, for the sake of assumption, everything else remains the same. The processing parameters, the stresses involved in the processes are identical. In that case, you probably have a higher tensile property with a higher spatial angle. Now, when it comes to fiber length is a typically difficult parameter. It's not just about 50% span length, or it's not about span length. It's all about, boils down to a very important but unfortunately ignored parameter of fiber friction. Friction is a function of spatial angle as well as the surface it describes, which in essentially is micronear. And of course, micronear and the cross-sectional, your cytoplasmic configuration of the cell level, and therefore the surface it describes naturally. All that will add to the friction between the fibers or to reduce the friction. So together, it's a function of the spatial angle as well as the surface it describes. Together, it describes what is known as the fiber friction, or the resistance to stress. Now, when you have that kind of situation, you really do not know, we really do not know what is the span length. Because span length, for all we know, it is an instrument, is an output of the instrument which evaluates a cluster of fibers. It doesn't individualize it to the single fiber state, although theoretically, yes, probably it looks at a wave and evaluates, okay, if the amplitude of the wave is within this particular domain, it is assumed to be single state fiber, but in reality it is not. So you could be having a naturally dense fiber cluster or slightly lower density, and that in turn could give you an output which will be misleading. So in essence, I am not going into the discrete levels of these fiber length, but more importantly, I'm looking at from a wave perspective as the process moves on, right up to the structure of the fabric. Even when we look at the fabric, it's not the yarns that we are looking at, we are looking at the orientation of the fibers, how the core has been formed, and how the migration has been happening. It's a constant state of migration that we are looking at, right across the fabric surfaces, right across the yarn surfaces, no matter what the cross-section of the yarn is. We are perpetually looking at core, we are perpetually looking at the peripherals, and we are perpetually looking at migration of fibers in clusters. And that it all boils down to spindle angle, and what is the angle you generate in the process, and more importantly, the fiber friction. So that it is the foundation for creating the process decision algorithm. Unless we delve deeper into the fiber dynamics in a Fourier transform, we will never be in a position to predict a process, and we will not be in the realm of engineering, where you engineer a fabric or you engineer a yarn. That is not going to happen unless we look at waves, look at fibers as a function of Fourier waves. I move on into the next slide. It is, of course, I just is a simulation of the fibers and structures. I'm just giving you a random simulation. If you look at the R square value for a quick refreshment, I mean, I will just refresh your memory. R square is basically a measure of how true the data is. Whatever your data is, how true the data is as per your curve slopes or curve configuration. So if the R squared is, let's say, 0.85, 0.86, anything above 0.8 will essentially mean that your curve is a fair amount of, it describes fairly the properties that are changing within the waves. And if the R square is lower than 0.5, 0.6, maybe like, for example, in this case, it is 0.4, 0.43, 0.42, which is on the lower side. It is significantly lower than what it should be. So 0.42 means, what it means basically, it boils down to the fact that we cannot predict the nature of the curve. This curve is typical of this particular population, but can we predict the curve for a future population, maybe after the nth instant of time? You see, our process is a continuous process. So we have to divide it into T1, T2, and so on, the time zones, the timelines. There's a time series model. In a time series models, when your R square is much lower, it essentially means you are not able to predict the nature of the curve in the for the nth instant of time. In that kind of scenario, your process prediction becomes an extremely difficult task. And that's probably one of the reasons why I am beginning the entire presentation with an extrapolated Fourier transform. My entire initiative is that my process is perfect, or I mean, if it is near perfection, if my process is improving, my R square should be improving. If my R square is, let's say, 0.8, 0.84, 0.85 of a wave, then it essentially means that I am in a prediction mode. I know exactly what will be the shape of the fibers on the nth instant of time after this initial lapse of data. That's what it is all about. Are we in a position to predict? As of now, we are nowhere near close to prediction. Nowhere near close to prediction. That's unfortunately one of the sad problems that the industry is facing. And therefore, you see right across the yarn industry, right across the weaving industry, we are perpetually struggling for getting the right productivity. We are perpetually struggling to get, oh, okay, which one is the best cotton mix? What this particular cotton will give me the right fabric? What is the costing and so on? So it's a struggle, it's an endless struggle with nothing in. Now, okay, coming back to the presentation, we were discussing about R square. Everyone can see this R square now on the screen?
Yeah.
If you see, the R square is 0.4386 of the first wave, and the second is 0.4276. So essentially what it means that the prediction of the shape of the curve at this particular point of time is just about 0.43 on a scale of 0 to 1. If it's closer to 1, is it visible, sir?
Yeah, visible now. Visible now.
Okay.
Yeah.
So as I was, let me resume the entire presentation all over again. This R square is a structure of the wave and how it predicts, how it fits. If I get an R square value of 0.84, 0.85 or close to 1, it essentially means that my wave is perfectly fitting and I'm able to predict what will be the shape of the wave approximately after nth period of time, nth time or n minus 1 time and so on. That's it. So what are the implications of this particular wave or the R square? The implication is if in a process my fibers are migrating or showing migratory behavior of a certain type, of a certain domain, then can I expect that this particular behavior will remain right across the process time? If the process time is a time series from the time 0, t0 to tn or nth time. So between the time series, of the timelines, can I get a consistent R square, which means my waves of the fibers right across the yarn and right across the structure of the fabrics will be by and large consistent. And that in turn will bring in the consistency in the process, which we are all seeking in terms of quality, in terms of productivity. So the entire presentation is all about controlling or improving the R square of the fiber migration in the process in a Fourier transform. Fourier transform is essentially all about periodicity of behavior. And it could have varying amplitudes, it could have varying wavelengths, it could have varying harmonics based on the frequencies of injection. So it basically boils down to bringing in a consistency of amplitude, consistency of wavelength variation, and more importantly, your wave characteristic or wave configuration. Whether my wave configuration is by and large consistent as described by R square. Now, what is a narrative on the discrete causal factors? Discrete, again, I repeat the word discrete. It's a discrete, we normally, discrete essentially means it is a standalone, mutually exclusive population. And we need to normalize it so that it becomes a representation of a continuity process, a process in continuity, or a continuum. The first, as I was discussing, the beginning of the presentation was fiber freedom as a key driver of structures. And fiber freedom is basically a function of surface and the spatial angle. And then the torque permeability. You see, as we go down into the yarn process and eventually into the knitting process, or for the matter, the ear-jet looms, it's all about the how much of torque can permeate into the structure of the yarn. That in turn will decide the eventual core of the yarn, which eventually, finally, will shape up the fabric and the garment. Of course, whatever the fabric is, I mean, the garment is a manifestation of the properties of the fabric. So torque is a critical parameter, which is again a function of fiber freedom and the ability of the fiber clusters to absorb the torsional deformation. So torque permeability is a narrative, which is a causal factor of the entire process chain. And then finally, the core formation. Theoretical models on core, there have been enough models, endless models, right, over the decades, over the hundreds of years probably in textile spinning. But we haven't yet found out the mathematical relationship between fiber waves and the cores and the structural formation of the core. And this is where the beginning of a new exploration in our process, wherein we are trying to predict. It's all about, if you look at the previous slide, we are looking at the structure of the wave, the prediction of the wave, which will eventually result in torque permeability, consistency in torque permeability, and the formation of the core. Which, if you want to describe the quality of a yarn or the productivity of a yarn, it all boils down to two important parameters. What is my permeability of torque right across, and what is my core? How good or how poorly the core is formed. These two parameters decide the fortunes of the textile industry right across the value chain, even up to the fabric. Perpetually or perennially we might be fighting for solutions for the garments or for the fabrics, but the essence boils down to what is my quality of core. So coming back to where we left, I guess we are on, right?
Yeah.
Okay, next slide, we are moving into reflectance function, where fiber freedom again is a key influence. Now we talk about, I'll just give you an attribute. If you look at the spreadsheet modeling later on at home or wherever, you will see the attributes are all well factored in, or clustered in. For barre, the typical barre or the color variation, we look at reflectance. Reflectance is a very key property, but unfortunately is not really well measured except in the HVI, and it's not really followed up right into the process. The reflectance is again a function of fiber freedom. How much is my fiber freedom? And that is what describes the surface of reflectance and the light reflectance. And that in turn, if you have variations in reflectance, you will have noticeable differences in the color tone, in the color uptake, and therefore you end up having patches of uneven shades, and eventually, probably in some cases, it also shows up as a barre. But primarily, it's all again function of fiber freedom. It's not about yellowness. It's not about anything else. What it really matters is what is my level of strain in the fiber, in the process. How much strain has developed in the stress factor, in the process factor, and what is my relative degrees of freedom as we move on from the card stage and right up to the pre-spinning stage. So,
Hello.
I hope everyone's around, right? Yeah.
Okay, you can continue.
Yeah. So I just illustrated. This is a vertical axis, which is a theoretical geometric axis of the fiber. We are assuming this is a geometric straight line, geometric axis, and if I see a natural fiber, what is the natural inclination? This is a torsion. This is the angle of torsion, which really matters more than anything else in my understanding, in defining the waves in the Fourier transform. And therefore, the torsion function governing the bulk work done to rupture. When you look at a bulk or a cluster of fibers, what is the amount of work done to rupture, and what is the define? It all defines the fiber freedom, migration from core to periphery, and so on. It all starts and begins from this angle, which unfortunately is not even measured as of now. It can only be assumed. I do the assumption based on my elongation. If you show me the data, if you give me a figure of elongation 6.5 and a length of around, let's say 32 mm, 2.5% span length is say 34 mm, and I know it's a 6.5 elongation, I would know, I can estimate that probably is around 40 degree or 38 degrees torsion angle. Whereas if the fiber elongation is somewhere around 5, 5.1, 5.2, and the same length of 33, 34, I would rather assume it's realistically the assumption would be somewhere around 20, 21, 22 degree torsion angle. So you have a torsion angle variance of 22 and 34, and the properties will not be identical. And you ask any spinner, the spinner will know from his experiences, well, 22 and 34 is just not a measurable value. But more importantly, if you look at these two cottons, the properties are way different. And therefore, it also shows up in spirality of the garments and the fabric skew and so on. So this is an essence which I was just discussing. I move on to the next slide. What are the determinants for barre or reflectance and physical migration? Unresolved axial torsion. Unresolved. The entire process in the yarn manufacturing is all about resolving stress, resolving torsion in the axial direction. That's what we are doing. That's what the card does. That's what the comber does. That's what, for the matter, right up to the pre-spinning stage, we are essentially looking at the axial torsion that is not resolved. If whatever unresolved or resolution we haven't resolved a certain torsion, it will show up in the form of either slubs, it will show up in the form of a host of problems in the yarn. host of quality defects in the yarn. And for that matter, it will change the structure of the core. And this is where the inconsistencies come in. Inconsistency is all about unresolved axial torsion, because the process itself is not adequately tuned in to remove the net torsion across the cross sections rather consistently. It isn't able to do that, and that is precisely where the problem arises. Then we have, of course, uncontrolled migration is a direct offshoot, direct resultant of unresolved axial torsion, because it will migrate wherever the stress differences are, the differentials are there. And then the strain, yeah, strain is a very important criteria for defining the fiber behavior. Strain is primarily a loss in elongation because of the stress, a partial loss in elongation, and a structural variation. Because when a strain is developed into a fiber, for sure, the cytoplasmic changes of the cell have already undergone a massive change, and therefore the fiber is permanently deformed. There is a cellular deformation which is permanent, which cannot be restored. And in that kind of circumstances, what really happens is the diuptake, you have a host of issues which are related to the surface characteristics of the cell. And it all begins with the strain differential, unresolved axial torsion, and what is the, you see, we were discussing about torque permeability, the second parameter. Torque permeability, if it varies, it will cause higher strains to be developed in the fibers or very low strain. So you have a random population with a segment where the strain is very high and another segment where the strain is very low. In that kind of situation, what do you think you will have? You will have a varying reflectance in the fibers, and eventually the dye uptake, the dye depth, everything will change. And that's where the problem arises. Especially for composite shades. Composite means you have, let's say, 4 or 5 shades going into that particular color. A composite color is not a primary color. It's not even a secondary color. It's a composite color, wherein you have various colors putting in, and then in that kind of, like, you might be having some metameric colors where when you reflex with light, it shows a different color, and the light is not there, it is dampened, you have a different color altogether. So you have reflectance properties which are significantly varying because of the variations in strain, the differential strain and the differential torsion. Having said all of this, I'm coming to the most important part of the presentation, is the card function, is the line of shear. I know it's a very difficult concept. Unfortunately, the textile industry, as of now, is still struggling with what really matters. And we are perpetually debating, this is a Trutschler card, this is a Rieter card, this is a LMW card, and this is the design, this is a 60 centimeter or whatever, the diameter, this is width, and so on. Endless debates in the textile world about the carding design. But what really matters at the end of the day is the line of shear, and that is something, unfortunately, is not really focused on in the textile industry, and that is where is the beginning of all our problems in the textile process. So what exactly, I will just briefly touch upon what exactly the line of shear is. Of course, it's as vast as the ocean itself. Line of shear itself is very, very complicated. It's an extremely difficult science, and I believe the understanding is yet shallow, even in the realm of card engineering. Well, having said all that, what exactly is the shearing line? I want to take you to the next slide, which is a visualization of what the line of shear is all about. I guess you will be able to figure out what this is. This is a cylinder, of course, and this one is the flat plane, the plane of the flat tops. The line of shear, I'm just giving an illustration. It need not be like this. It continuously changes. These are the coordinates. If I take a reference frame with the center of this axis, the vertical axis and the horizontal axis, the center right there, the center is a 0, 0 of a reference frame. With that reference frame, I will have certain coordinates of this particular edge. And another coordinates over there. So across these coordinates, you have this is at the nth instant. The next instant, you could have a varying of a different line of shear. Line of shear is basically, it all boils down to where does the flat penetrate, grip the fibers, and what is my axial torque of the cylinder, and how does it shear through the fleece of cotton. That all depends on the aerodynamic controls. It depends on a host of factors. And just quickly correlating, it's on the wire selection of wires and the management of the wires, or resharpening sickles, and what are the cross-sectional area described by the grip of the wire onto the cotton, and what is my density of cotton between the flat tops and the cylinder at any given point of time. And of course, how is the temperature dissipated? How is the temperature dissipation happening between the planes, so that you have a certain plane? Now, we might be assuming it's a 12 gauge. I mean, we are assuming that, okay, it's a 12 thou or 14 thou or X thou or Y thou. That's only an assumption, because with whatever we do, the gauges in a static mode, when there's a it doesn't really manifest in the dynamic mode. In the dynamic mode, there are a lot of air controls involved in the process. The thickness of the operating layer is massively different at every instant point of time, and then the wire cross sections are not really identical at all across the cylinder. And then, of course, the flat tops itself has got its own curvature, which can change instantaneously at certain cross sections or certain coordinates. And therefore, the line of shear is basically a resultant function of multiple factors of aerodynamics, the wires, and of course the flat plane, and therefore it shapes. But eventually, the whatever we were discussing about the cotton, like unresolved axial torsion, uncontrolled, strain differential, whatever we were discussing so far is all primarily a function of is determined by the line of shear. If the line of shear is too bad or too poor in effectiveness, it will be pushed right up to the flat tops. This one can probably move. You imagine the line of shear over here, where my cursor is. Just follow the cursor. If my cursor is like this, that means my line of shear is up there. You have a large cotton density or fiber density over here between the flat tops and the cylinder. For sure, your quality is going to deteriorate very, very sharply, and you would never know. Similarly, if my line of shear is coming down, just follow my cursor. If this line of shear is very close to the cylinder, what it really means is the fibers are strained. The fibers are subjected to a massive strain, to a massive torsion. And the strain differential, you can imagine, let's say there are two cards, identical design, everything remaining same. But one card is relatively, your line of shear is somewhere very close to the cylinder. Another card, same design, everything else remaining same. The line of shear, for whatever poor maintenance, has moved right up to the flat tops. What do you think will happen to this card sliver? You may endlessly check your neffs. You may continuously, perpetually check your neffs. That's not the end all and be all of the entire process of spinning. It's all about, boils down to what my strain in the fiber is. Obviously, the card where the line of shear is close to your cylinder will have a massive strain, and therefore it will be different from, fundamentally it will be different from the other cards. And that is where the beginning of your barres or color variation or property variation or even skew variation and so on, a host of factors. And all that is captured in the spreadsheet modeling. We'll talk about it. I don't know whether time will permit or not. We'll talk about it. But suffice it to say, this line of shear is the heart of the entire spinning process. That's first. And second is, of course, this is another complicated area. You may see so many designs like whatever I've done. This is basically a air scatter. Air scatter is when you have the cylinder rotating at, say, 500 RPM, 600 RPM, and the wire population these days is around 1,000 PPSI, around 1,100 or 1,000 or 980 or somewhere there between 900 to 1,100 points per square range. You have that kind of high density wires, and you have this RPM of around 550, 600. You will have pockets of air clouds which are not visualized. It will happen randomly, and this fiber is being subjected to that kind of areas, the aerodynamics. This is the aerodynamic of the card, wherein you see the clouds and this liquoring zone. This is the liquoring zone. I mean, my assumption this is the Doffer zone, and this is of course the undercasing and so on. So these air pockets are primarily the function of the dynamic gauges and a host of major areas of card engineering, which I'm not touching right now, is outside the scope. I mean, the time is a constraint. We can go on and on probably on this card itself, but suffice it to say that probably the air scatter is fundamentally changing your properties related to strain, related to torque permeability, or whatever we discussed in the beginning of the presentation. So, and then the axial congruence. Now you might have learned this is an axial congruence. Okay, we are assuming this is a straight line. I can draw a straight line, geometric straight line, congruence, perfect congruence. That's theoretical. In reality, what really happens is this entire material of the card, the structure, there are nanoparticles which are now completely displaced because of their massive rotational torque, which it is subjected to for hours together, 24 hours a day, 7 days and 7 days a week, and so on. So because of this constant rotational torque, you have the discrete nanoparticles right across the distribution of the surface of the card, the metallurgy of the card, wherein is no longer congruent. There will be an axis, there will be an eccentricity, where the axis will be slightly skewed from this congruent axis. And therefore, when it is skewed, imagine what will happen to the ear. Currents over here. What will happen to this line of shear? It will be haywire because of the lack of congruence. So it depends on what is my level, what is the eccentricity, what is the angle of deformation in the congruence, which will now lead to the air scatter and the pushing up of the line of shear. So this is where the complexity of the shear dynamics comes in. And no matter what your design is of the card, you really have to look into the critical maintenance of cards in order to achieve their right results, which unfortunately is still, we have a long way to go. Move on to the next card, next slide is a pre-comber draft. Of course, I'm just quickly moving in. This is like, I don't know, the population, I guess they are drawn in from fabrics and whatever, so it might not be of interest to them. But pre-comber draft is another critical area, is an element for crystallizing the final angular torsion and the related degrees of fiber freedom in the entire process. This particular parameter is not even looked into in the spinning process. Unfortunately, I'm using, again, very harsh words, but I know what I'm talking about. I have years of experience in the spinning industry, and when we talk of a financial transformation or turnaround, whatnot, it all boils down to these nitty-gritty of manufacturing process. If you're really serious, we have to look into the pre-comber draft, wherein we have to look into all whatever we are discussing to establish a very strong equilibrium of productivity and quality in order to achieve a financial turnaround. Okay, we'll come about it. We'll come to it later on. But suffice it to say, for the moment, pre-comber draft is all about removing the angular torsion and consequently related degrees of fiber freedom in the entire process chain. Okay, comber high intensity. I will not go into the written matter. I will go straight away into the drawing. Illustration is far more powerful. I believe so. And this is the cross section of the half lap of the comber. The comber is a very difficult machine to deal with, and the design is extremely complicated. And I believe a lot of research has gone into the designing of combers. But for the moment, we restrict ourselves to discussing what is my compressive arc. Compressive arc is, is a reciprocating mode. So as it reciprocates, the load factor moves from literally 0 at the point of reversal. This is the reversal point. The cursor is the reversal point. And then again from somewhere here. So in the reversal plane, you have a literally magnitude of 0 load to a maximum load of, it could be X Newton. So it's rotating, or it's rather fluctuating between 0 to X Newton in split seconds. Like These days, the comber speeds are around 500 sickles per minute. 500 sickles per minute. 500 times you are subjecting it to a massive load and to a zero load. Then the same fiber flees. So when you are subjecting it to the maximum load, what really happens is you are compressing the fibers. It's no longer an axial stress. It's no longer anything else related to longitudinal or lateral direction. It's compressive load, and therefore, and then again it just off. The load is literally off in less than a split second. So what it really means is these fibers are subjected to a massive compressive load, and compressive stress increases in the trough, of course, and domain for stress is extremely wide bound, because there is a moment when your fiber is absolutely with zero load, and another moment you have an extremely compressive load. Now, when you're applying the compressive, when you're applying the compressive load, what really happens is, again, the differential of fibers, differential of clusters. Some of the fibers in the cluster are weaker fibers, immature fibers. When they are subjected to compressive load, they will literally rupture, or even if they are not rupturing, they will still be sticking around. They will not go into the knot, the so-called waste of the comber. It won't. There is a reversal in the knot process, knot extraction process, wherein the weaker immature fibers could be waylaid by the longer material.
Just coming, sir. Yeah, visible.
Yeah.
Don't do the
So
power
as I'm
source.
saying, yeah, I'm continuing. Yeah, we are short of time. So compressive arc is basically what will decide whether there is a reversal of immature fibers into the parent fiber, parent fleece, and the so-called mature fibers might be finding their way into the null. So it's all about the management of the load in the compressive arc, which decides the functional behavior of the fabrics and the garments. Okay, when we come to now the spinning, we are looking at noise or waves. Primarily, you have the shafts, you have the end pieces, and they are vectors. They are the one plus and minus. Plus means I'm just giving it a plus direction, where you have the shaft section. Another is here, and the gap is A1. And if it is in this, from the left side, you are on the top, I'm giving it a plus direction. And here, the right is on the top, so it will be a minus direction. Again, like this one. This is an illustration of what I'm talking about, the vector direction. The vector direction I'm assuming is minus, if I'm assuming this one is plus. So this is the true situation of a spinning frame, wherein you have varying degrees of gaps between the shafts at the coupling point, and also the vector is also varying. Now all this leads into another series of Fourier transforms and the form of wave family in the ring frame structures, and this is critical. This is what we call the noise. Noise is if you are not able to predict the structure of the wave, as we discussed at 0.43, the noise is extremely high. Noise literally doesn't mean the noise that we conventionally say, okay, my decibel level is very high. It's not about the noise I'm saying. It's a mechanical noise. It's a wave. It's a mechanical noise, means the level of turbulence in a particular frame or in a particular family of waves. If you notice over here, I've given two waves just for illustration. One of the waves is a different configuration. Another successive wave is of a different configuration. So these massive changes, if they are significant, then it creates what we call the noise. And if you have very high noise level in the spinning frame or at the coupling points, of course, there are ways of solving them. There are ways of damping the waves, and there are ways of increasing your R square to make it more consistent. All that will eventually give you a better core of the yarn. You remember at the beginning of the discussion, we were talking about the core, the migration behavior, the fibers and all. So all that boils down to managing the waves in the spinning frame, managing the waves or the noise and the noise level in the waves. Okay. So if I look at the terminal stages of the presentation, allow me to jump because the garment determinants I will come at the end of my presentation. I'll first go into my thermodynamic influences for color. Color chemistry is one of the most critical elements in the entire textile manufacturing process. But unfortunately, we do not look at it from a thermodynamic perspective. And that's probably one of the reasons why we are perennially fighting for BASF, I mean, the better brands of dye stuff. We are looking at the very expensive reducing agents or the exhaustion agents and so on. And eventually the recipe of a very high quality of fabric, the recipe for the dye, dye recipe will be extremely expensive. The fundamental reason for all of that is we are living with inefficiencies in the thermodynamic process. What are those inefficiencies? Let me quickly explain you. The first level of inefficiency is the combustion inefficiency in a boiler, because the source of heat has got its furnace, it's got its refractory lining, and therefore the refractory lining determines, there's a Young's modulus of the refractory lining, which is a function of the strain developed in the refractory caused by the number of heats. Number of heats means, for example, your furnace has got a temperature or maximum available temperature of around 1000 or 800 degrees Celsius. Now beyond 1100 or 1200 degrees Celsius, it starts increasing the radiating losses. And more importantly, the structure of the refractory expands and develops a strain. And that's what the Young's modulus is. So in the next heat, one heat means you ramp up the heat from normal room temperature right up to, let's say, the peak value of 800 degrees Celsius in a furnace, in the boiler. And then eventually when the process is over, you bring it down to back again to the room temperature. So that's one heat. Room temperature to peak heat, and again back to the room temperature is one heat. So let's say after n number of heats, your refractory has already lost a lot of expansion by virtue of a strain. So when the thermal strains develop, what really happens is your radiation losses increase. And if you're supposed to achieve 800 degrees Celsius in the furnace, it might drop down to 500, 600, 400, or 450, 500. That kind of drops are are very, very possible, and they happen on a day in, day out basis in the boiler, and no one has a clue to that, except when you are looking at from an energy engineering perspective. That's a different ballgame altogether. But when we look purely at a textile perspective, for all I know, your boilers will have a very low combustion efficiency. And what does combustion efficiency means? It means simply that your temperature, which was supposed to be 800 degrees Celsius when the boiler was new, when the refractory was new, has now dropped down to 500 degrees Celsius. With that kind of, the operator has been instructed to maintain a pressure of, let's say, 10 bar or 8 bar. So he will now struggle to get 8 bar, 9 bar. He will just pushing a lot of fuel and make it, say, 10 bar. And then again it drops down to 8 bar because it cannot sustain itself. It sustains the pressure. Now what happens to your dyeing process? Your dyeing process gets affected very severely because the heat transfer, it's not able to achieve the kind of thermodynamic equilibrium during the dyeing process, whether it's a piece dye, whether it's a yarn dye, no matter what. The bottom line is you are losing heat in the liquor. And when that happens, what really is the outcome of that? The outcome is, it's when we talk of dyeing, unfortunately, we textile engineers do not really appreciate that, or textile chemists for the matter, they do not appreciate the most important factor that determines the dyeing process. And that factor is the kinetic equilibrium of the dye bath. And kinetic equilibrium of the dye bath is functionally determined by the ions, by the exchange of ions and the stabilization of the ions. Because that ion is a dielectric field. So I have written over here, Young's modulus and fuel combustible realization through dielectrics of furnace oil or air permeability. Okay, this is the combustion. Even in the dyeing, there is a dielectric field in the dye medium, determined or governed by the number of free radicals and the exhausting agent and also the reducing agent, and of course the dye itself. The dye itself will have got chiral values, chiral bonds. Chiral bonds are basically the oriented bonds, where you have both the positive and the minus negative orientation, and each of the free radicals are actually oriented themselves. So it's so difficult to break that free radical. That's what a chiral bond is all about. And then there's a bond strength and a bond moment. So it all boils down to what is my ionic concentration? It cannot remain the same at varying thermal levels. When the thermal levels change, when the enthalpy changes in the dyeing medium, you essentially end up in a situation where your ionic concentration changes, and without you knowing. And that's probably the main reason why our textile chemists will be fiddling about, we're tinkering on. You add some reducing agent, or keep on adding some exhaustion agent. Maybe you change the recipe based on the uptake. The chemistry doesn't remain consistent. The primary reason for all of that is you don't have a consistent ionic concentration, because the heat itself is not uniform. It might drop down to 8 bar. No one really knows, or rather, no one would care. Okay, it's 8 bar. What's the big deal? And then it moves on to 10 bar. But the quantum of heat transfer between 8 bar and 10 bar is massive. And all that is happening because of low combustion efficiency in the furnace, because of refractory. So there is an intrinsic link between thermal engineering and the dyeing of fabrics, which unfortunately is not very well appreciated in the textile industry as of now. I'm again using strong words, and I know what I'm talking about based on my experiences. So this is one of the major reasons you end up having a very expensive dye chemistry. You end up having less than satisfactory dye color tone and dye uptake and so on. And how that gets reflected, we can really figure it out. Okay, and just, you later on at home, you might read through contaminants and steam reading, and these are all thermal engineering aspects. I'm not dwelling too deeply into this, because this is probably beyond the scope of the present audience. But nevertheless, these are very important derivatives which need to be looked into. So now, coming to the influences for color 3, managing the dielectric field of the liquor is a critical application. I just finished mentioning that influences color strength, fixation, and dye affinity, the fastest properties. Now, most of the textile mills, textile laboratories, textile chemistry laboratories always have what you call the software for evaluating the color coordinates, right? Whether it's a composite color or it's whatever colors, primary colors, secondary colors, and so on, you have the resultant color coordinate which the software gives you. But what is more important for me to understand is, for example, you are dyeing a particular shade, let's say navy blue shade. I'm just giving an example. Navy blue shade, batch 1, batch 2, batch 100, batch 150, and so on, batch nth. Now, what are my color coordinates? The resultant color coordinates, the color coordinates of the nucleus of the scatter. There will be a color scatter, right? And from the color scatter, you figure out what is my nucleus and what are my coordinates of the nucleus for the batch 1, batch 2, and so on. The coordinates, for all we know, will be changing. But if you say we have the funny figures, delta E, okay, it was less than 1.2, 1.1, delta E, 1.5, and so on. Okay, 0.8, 0.7, we are happy. It's not the case. More importantly, it's not really, even if you get 0.8, 0.7 and the delta E, you might still get a position where two different garments of the same batch, there are tonal differences. There are, and from my experiences, there are significant tonal differences, depth differences, and of course, and all these lead to the major factors, the color coordinates. And color coordinates are a function of dielectric field or whatever we just discussed. And the best way to figure out is when you map it and when you start training it and you figure out what is my color moment. Color moment is what is my span of the deflection between batches. That will tell you what is the strength of the liquor. So liquor strength is primarily a function of dielectric field. So we need to figure out a way how to measure the dielectric field, record it, trend it, and then also record and trend the performance of the baller with various aspects. So it's a blend of thermal engineering and the chemistry going into the dyeing process, which will eventually decide consistency, and also it will significantly reduce the cost of dyeing. That is a major derivative. You can end up having a reduction of 25 to 30%. I have experiences that I can demonstrate anywhere and wherever and whatever context. That 25 to 30% of the saving potential is there in the cost of dyeing, and merely looking at the combustion factors and the dielectric field of the leaker. Data collation and okay, now before I move on into the garment final stage, I would like to look at the most important area. We call it, you remember my presentation is all about machine learning and artificial intelligence. It sounds great. These days it's a hype to talk about AI, it's talk about ML, but no one really has a clue. I'm not even talking about the textile industry, even the computer industry, or for the matter, the information industry or the IT industry. They have had the hype of all machine learning and AI and so on, for every aspect, from COVID, from wherever. But really, very few people really understand what exactly machine learning and artificial intelligence is, more, and even less so in the perspective of manufacturing. Manufacturing is a complex engineering, and it requires a lot of alignment of models, alignment of mathematical models, alignment of relationships. Like, for example, I just gave you the instance of the dyeing process. Dyeing process is a function of the dielectric field in the liquor, and also a function of the steam, the quality of steam or quality of heat. So these are two diverse processes which have to be understood, which have to be learned real time. Learned real time means you have some indicators in the process. Those indicators are giving you a data. That data has to be collated and trended, and then you have to establish a mathematical relationship between, okay, if I have 10 bar pressure, this is my heat generated, say 180 degrees Celsius or whatever, XYZ, and this is my ionic concentration at a certain heat level, and this is my dwell time of the dyeing curve, this is my the temperature curve dynamics, and based on that, what is my output and what should my prediction. If these changes, if any of these parameters changes, these are the major influence clusters. So that's all about machine learning, but it's a complex subject. It's not really easily understood the way we want to project. No, it doesn't work that way. Anyway, coming back to our textile engineering, it's all about data collation and interpretation. Where does this happen? Optical and gravimetric. So you see, our textile processes are very complex and very beautifully captured. Nowhere. I've been working in multiple industries, not just textile. I've worked in at least 15 to 17 different domains. But I believe, not just because I come from a textile engineering background, but more importantly, I strongly believe, based on experiences, that your imaging, the way the image analysis is done in yarns at the autoconers using Worcester and or the quantum or whatever, they are the most complex I have ever seen in any of the industries, for that matter. So it's really complex, and we are lucky to be gifted with such kind of technology. But unfortunately, the interpretation of that technology and the utility function of that technology is lacking very seriously. And that's probably one of the reasons why the textile industry is not performing. You can have a wealth of information in the Worcester quantum or Lofe or wherever you look at, because they are measured optical and gravimetric measurements with the yarn clearing systems. You have various fault levels. I know I've mentioned that into the what we call the spreadsheet modeling. Now, if you look at the Lofe, or for example, the quantum, let's look at quantum for the matter, for the sake of argument. If you look at the quantum systems, you have both the optical and the gravimetric way of measuring the faults, and the faults are classified. Now, again, please hear me out very, very with a full concentration, because you might miss out the bigger picture. At the beginning of my presentation, I told you it's all about Fourier transforms, the entire fiber population, and how it moves in waves. In the yarn also, it moves like waves. And the imaging is basically a capture of the waves. When you look at the online data, you will look at A0, A1. These are discrete, okay? We have made it discrete because our thinking is always discrete. They are not moved. The textile thought has not moved into the continuous mode. It's still in the discrete mode. Therefore, the quantum, these guys are what they have done. They've given you A0, A1, A2, and so on. Faults, the typical, the conventional classified faults. No, it doesn't work that way. Trust me. I tell you from experience, it doesn't work that way. If you have an A0 slab, it actually migrates a function of your fiber configuration, the fiber degrees of freedom, which determines what is my A0 level and how it migrates. What is my core? How does a yarn migrate? All that now brings in a shift from A0 to A3, maybe B0 to B3, and there is a constant shift of fibers and a constant shift. Those shift of the fibers, the paradigm shifts of the fibers, are what define your online values of your discrete measures. C1, C2, C3, D1 and D2. And even the thin falls, they look at, oh, long thin, medium thin, and so on. We have to change the mindset and look into it. It's a real-time wave which we are looking at it. And we look at the data that the scatter of the defects, that scatter is telling you how the waves are migrating. Look at that and create a mental, what do you call it, sinusoidal curve. And probably not even mental. If you give me the data, I'll create a wave and a real-time wave for you. From the wave, you will know what is my R square, whether it's predictable, whether the shifts are happening across period timelines in a time series model. And therefore, you are able to predict what is going to happen in your dyeing process. Because the dyeing process is basically a function of dye uptake and dye affinity. It all boils down to what is my configuration, what are my cluster configuration, how the migration has happened, how the waves have happened. It doesn't boil down to a single file length, no way. So it's cutting the long story short, it all boils down to interpreting the online data in the form of waves, then doing the statistical inferences, statistical analysis of the waves, and figuring out what is my degree of prediction in the wave physics. It's actually wave physics. It's all about wave physics. It's a mechanical wave, it's an electrical wave, electronic wave, a signal wave, whatever. At the end of the day, it's a wave physics. And we have to treat the subject of textile engineering as an extension of wave physics. Fine. You look at process linkages, mentioned over here, process linkages are discrete and normalized for predictive controls. You cannot predict in discrete mode, never. It's not possible in mathematically. Statistically, mathematically, whichever. It is a stochastic process. What is a stochastic process? Stochastic process is a probability function. What is my probability of an event, of an occurrence, of a fault, based on what has happened before and what is going to happen now. And I have to predict what has happened. That's a stochastic process. And that stochastic process can never be discrete. Whatever discrete data you are there is all misleading. You look at, oh, my U-star is 8.3 and now it's 8.7. What has happened? It is not about boiling down to discrete figures. It's all about waves. Fine. That's what the online values are. That's what the Loffe quantum is. And believe me, friends, if you look seriously at quantum data, you can predict the entire spinning process, entire fabric manufacturing process, dyeing process, and even the garment process in your AC cabin. That's it. In your air-conditioned cabin, you look at the data and you can predict this is what is happening. You look at the car, you look at this. That is exactly what I want to project or what I want to do. And that's the algorithm is all about. Fine. I think, let me get back to what we are discussing. So I saw garment online data interface, assure process control, and the product change for online monitoring and quality data in yarns. Product economy is nothing. Economy is a function of quality. If you are churning out, if you're spinning a good quality yarn, if you're spinning a very good quality yarn, for sure you are getting a high productivity by default. You don't have to run around, shout at people, howl at people, do all sorts of whatever we do normally in textile industries, and you don't have to. Product economy is functionally driven by the quality, again by the waves. You manage the waves and you get an excellent productivity. And that's true for the weaving looms and the knitting as well as the garments. You just don't run around. You really have to focus on the control of the process. So I believe It's almost 8 o'clock, and value engineering is a mathematical process. And what I would request to the audience is, of course, the time was very short. I sent you in the emails today, this morning. I would request you to go and study the spreadsheet modeling, and maybe you can later on you can generate n number of questions, and it will be very, very easy. I mean, it will be my privilege to answer you. And if you want practical demonstrations, practical solutions, give me any factory as a challenge to the entire textile community. Give me any factory in whatever shape, whatever technology, and I will demonstrate you what is the transformation is all about. What are we talking about? No matter how run down the machines are or how state of the art the technology is, I don't care. It's all about understanding the process. It's about doing the right engineering to get your productivity and get quality. This is a challenge from a professional challenge to the entire textile industry. Fine. Having said all that, I am ready for questions. N number of questions. This is all now a open session for all of you. I'm ready for your question answer session, sir.
Now anyone can ask the questions. There are questions, sir.
Yes, sir.
I'm reading a question for you, sir.
Could you ask someone to chat it if possible? If not, it's okay because your sound. Okay, anyway.
Already written in chat. Already question written in chat.
Sorry?
Already question written on chat.
Yeah. No, if it is chat, it will be convenient for me. But you can
already,
speak up.
Sir, already question is available on the chat.
Okay, yeah. I'm ready for the questions for the chat.
Sir, the question is already available. Check it, please.
Oh, okay. Where do I check now?
Just click on chat. People के साथ में chat है sir. People के साथ.
I'm seeing. Is there a method technique to define line of shear accurately? Yes. Let me answer it. Can the chat be visualized to everyone around?
Yeah, it's a visual to everyone.
It's visual to everyone?
Yeah.
Oh, excellent. The most important measure to figure out the line of shear is the frictional quantum.
Send it to everyone, sir. Send it to everyone.
Frictional quantum as measured by the TC07 card. Trutschler TC07 card, if you have any one of you have seen it, it has got temperature sensors which can measure the temperature distribution right across the curvature of the cylinder, real time, continuously, and that data will tell you exactly how is the line of shear happening. If the temperature is increasing, it essentially means the frictional value is very high. If the temperature is high, it means that your line of shear is towards the flat tops. It has increased. It's very poor. And if your temperature is going down, it means it is closer to the cylinder. So even if you do not have a TC07, it doesn't matter. Even if you have a LR 1/3, a very old model, maybe 50 years or 40 years or 30-year-old model, it doesn't matter. What you need to do is take a temperature gun. These days, people are taking temperature guns to evaluate your own temperature. Leave it alone. Take that temperature gun. Look at the temperatures from your P1, P2, P3. P1, P2 is, of course, the flat tops in the cylinder. You look at the other gauge points and then look at across the flat tops. Just measure the temperature. What is the temperature on the surface of the flat tops at any given point of time in a dynamic mode? Let's say your card is operating at 30, 35 kg or 50 kg, whatever the kg per hour. Okay, your cylinder is, say, 500 RPM or 560 RPM. It's in a dynamic mode. Then you start measuring and trending it, and you see between the cards there will be a variation. There will be a map of the temperatures. That is, the temperature is representing your. It's a temperature curve. Is a direct representation of the line of shear. Is that okay? What else? I see only one question.
There is one question from Mr. Chatterjee, and then let's have question from Lady Irwin College and ATDC also.
Okay, how shear forces are responsible for hook generation in carding and how it can be solved. Excellent. Now, let me explain it. If you remember, hook generation is a function of one, natural torsion of the fiber. If you remember, when we were discussing the slides, there was something called a natural torsion of the fiber. How do you determine it? If your fiber, example, fiber elongation, sorry, is 6.5% versus another sample which is 4.8%. Then 6.5% can be estimated to be having much higher hooks, both leading and trailing. Then sorry, I didn't get the question. Leading and trailing. Now, then the comment on this. Okay, line of shear, if it is closer to the cylinder as indicated by lower frictional heat and temperature, then the percentage of hooks is extremely low. Inflated coordinates of line of shear will increase unopened fibers and hooks concentration. Now the next question is, someone was asking spatial, how shear forces are responsive. No. The most important measure to no. Where is that? Hook no. Please comment on the association of spatial angle of molecular chains and breaking elongation of a fiber. Higher spatial angle requires greater quantum of work done to axially linear coordinates and consequently either develops secondary creep at a delayed time or brings in rupture and fatigue at a delayed timeline, thereby registering higher elongation percentage. Although Please do not be misguided. Higher elongation doesn't mean higher elongation does not necessarily mean better compressive strength. This is a very important derivative for all the audience. Please understand, you might be guided, you might be getting a very high elongation. That doesn't mean anything. The reason is elongation can also happen because of the spatial angle. If the spatial angle is very high, molecular, as you rightly pointed out, whoever, Amal Chaudhary, you have rightly pointed out what is the association of spatial angle of molecular chains and breaking elongation. You might register a higher elongation with a higher spatial angle, but that doesn't mean your compressive load is higher. Compressive load is functionally determined by the spatial compactness, spatial density, rather than the spatial angle. Angle is only related to elongation. Higher the angle, higher should be ideally the elongation, depending on the orientation. Otherwise, if the orientation, natural orientation is already deflected, it could bring in stronger rupture, a quicker rupture cycle time. So rupture and elongation are two different parameters. Yeah.
Can we have questions from Dr. Deepali and Professor Deepali and Dr. Sheetal from Lady Irwin College?
Okay, what's the question?
Can you unmute them, Dr. Mukesh?
So
Yes,
they
Dr.
they have to unmute their own.
आप unmute कर पाएंगे क्या?
नहीं सर, वो खुद करेंगे. अनम्यूट उनको खुद करना होता है.
अच्छा.
Professor Sheetal, you can unmute yourself and then speak it out, please. Professor Sheetal. Professor Sheetal, are you getting?
Yes. Can you hear me?
Yeah, sure.
Any question? Lady Irwin College?
Yes, Dr. Debasish, I think it was a wonderful presentation. But since we are not from an engineering background, so it'll take a little while for us to absorb what you have said, and definitely we'll go through it, and we will get back to you with any questions if we have, maybe at a later point of time, if that is okay with you.
Yeah, of course. I am always available. Through Mr. Shaleshji, you can just direct it to me, or you can direct it to me. You have my email IDs. You can just send me an email.
Yeah, but it was very, very interesting to see how machine learning and AI is being used in these processes to understand each and every aspect of the engineering processes of fibers and textiles.
Thank you, Dr. Sheetal.
Thank you so much.
Professor Rastogi, are you online? Can you unmute yourself?
Yes.
Sorry, Mr. Koji?
Yes. Dr. Debasish, thank you so much for this presentation. But as just mentioned by Dr. Sheetal, we would take some time because this is not where we dwell in, and so I go through your presentation once again, the slides, etc., that you have sent, and maybe we will come back to you later on. Thank you so much.
Yeah, thanks. If I would rather advise Dr. Sheetal as well as Dr. Dipali to look into the spreadsheet modeling as well, because if you are dealing in textiles, you are dealing in fabrics, you would be probably interested in looking at how the fabric behaves, and the spreadsheet model tells a lot of story, or whatever we were discussing in this presentation.
Yes.
Yeah, thanks.
Professor Debasish, it has been an excellent presentation, but it's turning many theories upside down, and it has been a long way since Pierce postulated his closed geometry equation in 1930 or something. So I think it's high time this theoretical research is also put into applied domain, and we come out with some solutions.
No, what I would be requesting Mr. Kaushik and Dr. Vinod Shanbag and the entire team for the matter, is if you have some practical problems from the industry, and I would be more than ever ready to field them, solve them, and as I told you, probably change the processes
Sure,
for good.
sure. We are open to it. But you see, what typically the man with the money, he will have to put it in very simple terms to him. So,
Thank you, Mr. Koshi.
And Dr. Chatterjee, are you there? Dr. Chatterjee? मुकेश जी चटर्जी साहब हैं क्या?
जी सर हैं सर.
उनसे पूछ लीजिए वो if you can wrap it up with a vote of thanks.
Chatterjee sir.
Yes.
Chatterjee
we are really grateful to Dr. Debasish Banerjee for giving a nice presentation. Actually, many of fashion designing students, for them it is a slightly upper, they're going upper of the head. But it is at the outset, I am seeing that this is a very useful topic he has delivered, and many scientists or many faculty members definitely will be benefited to deliver this kind of talk. So thank you very much, Banerjee, and
Thank
I
you.
hope that whenever you will be in India, please do come and to visit our institute and present your topics to our students and faculty members. Thank you, sir. Thank you.
I visit India for 2 weeks only during Christmas. That's okay. Thank you very much, Mr. Chatterjee, for your the rest of the faculty.
Dr. Kumar, any closing remarks from your side?
Sorry, I didn't get you.
No, I was checking with Dr. Shanbag if any closing remarks from his side. Okay, we'll wrap up the session now.
Yeah, okay. Dr. Banerjee, thank you very much for the professional contribution that you have made. I'm sure you will receive a lot of queries, questions by email or WhatsApp, and hopefully you will have the time to answer them in the best interest of the students and faculty. Thank you once again, and I would like to also acknowledge the contributions of Dr. Mukesh Kumar, Professor Chatterjee, and Mr. Shailesh Kaushik, and thank you all. And we also acknowledge the participation of Lady Irwin College in this event. Thank you all, and good night.
Thank you.
Thank you, sir. Thank you, Dr. Mukesh.
Thank you, Dr. Mukesh.
Thank you. Thanks a lot, sir. Have a great day.
Bye.